Concepts common to small-angle X-ray scattering and small-angle neutron scattering are described in the overarching lemma small-angle scattering. Small-angle X-ray scattering is a small-angle scattering technique where the elastic scattering of X-rays by a sample which has inhomogeneities in the nanometer range is recorded at very low angles. This angular range contains information about the shape and size of macromolecules, characteristic distances of partially ordered materials, pore sizes, and other data. SAXS is capable of delivering structural information of macromolecules between 5 and 25 nanometers, of repeat distances in partially ordered systems of up to 150 nanometers. USAXS can resolve even larger dimensions. SAXS and USAXS belong to a family of X-ray scattering techniques that are used in the characterization of materials. In the case of biological macromolecules such as proteins, the advantage of SAXS over crystallography is that a crystalline sample is not needed. Nuclear magnetic resonance spectroscopy methods encounter problems with macromolecules of higher molecular mass. However, owing to the random orientation of dissolved or partially ordered molecules, the spatial averaging leads to a loss of information in SAXS compared to crystallography. Applications: SAXS is used for the determination of the microscale or nanoscale structure of particle systems in terms of such parameters as averaged particle sizes, shapes, distribution, and surface-to-volume ratio. The materials can be solid or liquid, and they can contain solid, liquid, or gaseous domains of the same or another material in any combination. Not only particles, but also the structure of ordered systems like lamellae, and fractal-like materials can be studied. The method is accurate, non-destructive, and usually requires only a minimum of sample preparation. Applications are very broad and include colloids of all types, metals, cement, oil, polymers, plastics, proteins, foods and pharmaceuticals, and can be found in research as well as in quality control. The X-ray source can be a laboratory source or synchrotron light, which provides a higher X-ray flux. SAXS instruments. In an SAXS instrument, a monochromatic beam of X-rays is brought to a sample from which some of the X-rays scatter, while most simply go through the sample without interacting with it. The scattered X-rays form a scattering pattern which is then detected at a detector, which is typically a two-dimensional flat X-ray detector situated behind the sample perpendicular to the direction of the primary beam that initially hit the sample. The scattering pattern contains the information on the structure of the sample. The major problem that must be overcome in SAXS instrumentation is the separation of the weak scattered intensity from the strong main beam. The smaller the desired angle, the more difficult this becomes. The problem is comparable to one encountered when trying to observe a weakly radiant object close to the Sun, like the Sun's corona. Only if the Moon blocks out the main light source does the corona become visible. Likewise, in SAXS, the non-scattered beam that merely travels through the sample must be blocked, without blocking the closely adjacent scattered radiation. Most available X-ray sources produce divergent beams, and this compounds the problem. In principle, the problem could be overcome by focusing the beam, but this is not easy when dealing with X-rays and was previously not done except on synchrotrons where large bent mirrors can be used. This is why most laboratory small-angle devices rely on collimation instead. Laboratory SAXS instruments can be divided into two main groups: point collimation and line collimation instruments. Point collimation instruments have pinholes that shape the X-ray beam to a small circular or elliptical spot that illuminates the sample. Thus, the scattering is centrosymmetrically distributed around the primary X-ray beam, and the scattering pattern in the detection plane consists of circles around the primary beam, Owing to the small illuminated sample volume and the wastefulness of the collimation process, only those photons are allowed to pass that happen to fly in the right direction. The scattered intensity is small and therefore the measurement time is in the order of hours or days in case of very weak scatterers. If focusing optics like bent mirrors or bent monochromator crystals or collimating and monochromating optics like multi-layers are used, measurement time can be greatly reduced. Point collimation allows the orientation of non-isotropic systems to be determined. Line collimation instruments confine the beam only in one dimension so that the beam profile is a long but narrow line. The illuminated sample volume is much larger compared to point collimation, and the scattered intensity at the same flux density is proportionally larger. Thus, measuring times with line collimation SAXS instruments are much shorter compared to point collimation and are in the range of minutes. A disadvantage is that the recorded pattern is essentially an integrated superposition of many adjacent pinhole patterns. The resulting smearing can be easily removed using model-free algorithms or deconvolution methods based on Fourier transformation, but only if the system is isotropic. Line collimation is of great benefit for any isotropic nanostructured materials, e.g., proteins, surfactants, particle dispersion and emulsions.